Hello, and welcome to today's video. Today we're going to be talking about combining functions along with composition functions, and we'll go through a few examples of each case. It will be a shorter video, so without further ado, let's begin. So, combining functions. So the simplest way to combine functions is just to use their arithmetic properties, that is adding, subtracting, multiplying, and dividing. And I will write them down for you so we can discuss them further. So f plus g of x is equal to f of x plus g of x. F minus g of x is equal to f of x minus g of x. Fg of x is equal to f of x. Oh, that's f of g. G of x. And lastly, f divided by g of x is equal to f of x over g of x. So these are just some properties of functions that we can combine them using arithmetic operations. So let's say, for example, I have f of x is equal to x squared plus 2 and g of x is equal to x. Then we can say f plus g of x is just equal to x squared plus 2 plus x, meaning x squared plus x plus 2. So very straightforward, it's not very complicated. And one other special case we can consider is when we multiply a function by its scalar. So to demonstrate, so let's say we have c of f of x, that can be represented as c of f of x. Great, so let's look at an example quickly. And the example will be similar to the one we just computed. Let's say f of x is equal to x squared and g of x is equal to x plus 2. Then we can say f plus g of x is equal to x squared plus x plus 2. So exact same as what we did previously. But what does this look like graphically? What does f of x, what does f of x and g of x and f plus g of x represent graphically? So if we hop onto Desmos quickly, we can get a visual representation of what these three graphs look like. So we have x squared, which is the red graph, x plus 2, which is the blue line, as well as x squared plus x plus 2, which is our summation, f of x plus g of x, as the green line. So we can kind of see that the green line, our summation function, is just the summation of the values of f of x plus g of x. So if you look at 0, we have f of x being x squared is 0 right here. And the blue line right here, we see that at x is equal to 0, we have the value being 2. And the value for the green line is also 2, which makes sense because 2 plus 0 should be 2. If we look at another point, for example, let's say we let's go to right here. X is equal to 2. So at x is equal to 2, we have both x squared, f of x, being equal to 4, and x plus 2 as well equal to 4. So we can see that the value of the green line is 8. Since f of x is equal to 4 and g of x is equal to 4, then f of g of x, f plus g of x should be equal to 8, which makes sense. So you can just see that this is this f of plus g of x is just the summation line. And if we were to do f minus g of x, we would see that it's also just the subtraction of f from g of x. The value would be just a subtraction. So it's pretty intuitive. It's not very difficult to understand, but just know that this line, this graph represents the summation of the two quantities, or the two functions. Great, so the next topic I want to talk about is composition functions. So composition functions. So A composite function is another way in which we can combine two functions to form a new function, and I'll define it for you quickly. So if f and g are functions, then the composite function can be defined as follows. G of x is equal to f of g of x. So it's not too complicated. This is just the notation when we say the composition of f of g of x. So essentially we're plugging in another function within a separate function. So to do that, and I'll do the other case, we can have g of f of x, which would be of x, and in this case we have g being the outer function and f being the inner function. So to do a quick example for you so that you can understand what we're doing, let's say, put an example, let's say that we have f of x is equal to 3x and g of x is equal to x squared, or sorry, let's do 3x squared. Then we can say that f of g of x, that is equivalent to, we'd have 3, and then you plug g of x into x, you plug g of x back into f of x, so you'd have 3x, and that x is actually 3x squared. So you can see that we plugged in this value into this x. So initially we had this 3x right here, but we plugged in g of x where x would be. So that's the composition function. Similarly, we can go, if we simplify that, that becomes 9x squared. We can also go g of f of x. We can say that this is equal to 3. And now we plug in 3x, and all of this gets squared, leaving us with 27x squared. Again, we had, this is our initial function, and we plugged in 3 of x into x squared. So that came into here. So again, not too difficult of a concept to grasp. You're just using two functions and you're combining them together. And it's very straightforward and intuitive to understand what we're doing. One thing to note is the domains of composite functions. This is very important. This is where I see a lot of people get tripped up in when working with composite functions. So when we're dealing with the domains of a composite functions must keep the domain of the total combined function as well as the function we're composing with. Meaning, we need to understand the domain of, if let's say we're taking the composition function of f of g of x, we'll need to understand the domain of first g of x, as well as second f of g of x. This is because since we're using g of x on the inner side of the function, its domain must be held first, and then when we compute f of g of x, then we can also make sure that that domain is held true. So what do I mean by that? Let's look at an example quickly. So given f of x is equal to x squared and g of x is equal to root x, find f g of x. Great. So we know that f of g of x is simply f of x, or f of g of x. Well, that is just represented with root x squared, since we have x squared initially, and we plug in root x into x squared. That gives us x. So if I said, what is the domain? You may be tempted to just say, well, okay, well, the domain of x is negative infinity to infinity, since we have no restrictions on x. It's a continuous function. However, this is not the case. That is not true. We need to also compute the domain of g of x. We see that the domain of g of x for the function root x, the domain is 0 inclusive to infinity. That's round brackets. And you might be wondering, why is this the case? Well, let's say we wanted to compute f of g of -2, right? You could say, okay, well, f of g of -2 is just equal to -2, since we have x being f of g of x, right? So since f of g of x is equal to x, we can say that, and I'll just flip the order around so it's more intuitive. But you may think that this is true. However, this can't work. Since we said that g of x is equal to root x, we're not able to compute root of -2. That's not possible. That's not a real number. So that can't be the case. So we actually have to restrict g of x and our overall function to follow the restrictions of g of x. So we can say that the domain f of g of x has to follow the domain of 0 to infinity, since g of x is not defined for all real numbers. It is only defined for this specific domain. Great. So let's do another example. We'll do f of x is equal to root x minus 1, and g of x is equal to x squared. So let's compute f of g of x and g of f of x and find their domains. Great. So to start, let's do f of g of x. That is equivalent to f of g of x, which is equal to, so we have f of x being our outer function, so we'll have x squared minus 1. So first, to compute the domain, we see that the domain of g of x, so g of x has a domain of all real numbers, so there's no restriction to g of x. Great. On our final function, f of g of x, we see that we must have x squared minus 1 being greater than or equal to 0, since it's under a square root. So what we can do then is draw a number line right here because we're going to need it. But let's simplify this inequality expression quickly. We can do x minus 1, x plus 1 is greater than or equal to 0. And if you recall from our study of inequalities, we need to break these into 3 different test cases to understand the function behavior between each of the roots. So when we have a value of x, and let's call this x, less than -1 in this domain, we're going to have this being negative and this being negative, which is positive. So this is good. And likewise, in the first, the first, I guess, the domain from 1 to infinity, between 1 to infinity, we'd have positive value because both of our roots are positive. But in between the -1 and 1 value, we'll have a negative domain. So we're not able to include these values in our domain. So we can say then that our domain is x, for x, sorry, the domain the domain for f g of x, that would be negative infinity to negative 1, and we can include the endpoints. And we have the union of 1 to infinity, and that would be our solution. Great. Now for g of f of x, this is equal to g being the outer function and f of x. Great. So to compute this, we then get that we have root x minus 1. Oh, that's not minus 1. And we have all of this squared. So that leaves us with x minus 1. So we need to check the domain of first g of x. So the domain of, we need to check the domain of f of x, because f of x is the second function in this case, right? So we need to make sure that this domain is held. So to check the domain of f of x, the domain is x minus 1 must be greater than 0. Therefore, x must be greater than 1. So that's one of our restrictions. And note, when we're doing this, we must take the most restrictive domain. It's the domain that allows all possible values. We can't take a domain that allows some values for the composite and all the values for the the function that's being composed with. So we have to take the most restrictive domain. So we know that f of x must be greater than 1, and f of g of x, that has no restriction on the domain, so negative infinity to infinity. So then our final result will be that x, the domain for this value of x, must be between, and this should be greater than or equal to, will be between 1 to infinity. That's our solution. Lastly, we're going to do one more example. So we're going to have g of x is equal to 1 minus x all over 1 plus x. Let's calculate g of x. So it might be confusing, but again, it's not complicated at all. We're plugging in g of x into the equation of g of x. So what did this look like? Well, we say that that is equivalent to g of x, g of x, which is equal to 1 minus x, because we're just plugging in the function wherever we see an x. And we have 1 plus 1 minus x, 1 plus x. So not that bad. We just need to simplify this. Well, it turns out this is very easy to simplify. So on the top, on the numerator, we're going to pull everything under one common denominator. So 1 plus x minus 1 minus x, and that's under 1 plus x. Do the same thing on the denominator, 1 plus x, and this is plus, I'm going to put brackets around that, 1 minus x, and again under 1 plus x. Simplifying everything, we'll get on the numerator, well, we'll have 1 minus 1, which is 0, and x minus negative x, which is plus x. We'll have 2x all over 1 plus x. On the bottom, we'll have 1 plus 1, which is 2, and x's cancel each other out, 1 plus x. And then flipping this to form that we can use, 1 plus x. Again, this is just basic algebra right here. And I guess to show my steps, if you have, and I'll do this in red for you, if you have an equation in this form, you can say that that's equivalent to AB by BC, basic algebra. Yeah, if you need to do a little bit of a recap on that, that's totally fine. But essentially, doing this, we can say that, and I'll bring this here, this is equivalent to, we have this canceling and this canceling, and we have these canceling. This is all of equivalent to x. So this kind of nasty equation all just leads to x. So we can say g of x is equal to x. And the domain, well, you might be tempted again to say that the domain is x goes from negative infinity to infinity. However, this is not the case, because even though this is our final function, it's a continuous function, that we have these initial restrictions. So this function needs to be satisfied. So our domain actually is when 1 plus x is equal to 0, we can say that x is equal to -1. So all values of this function are defined except at this point. So we can say that our domain is negative infinity, that's a terrible infinity, that's even worse, negative infinity to -1, uninclusive, and -1 to infinity. This should be a union. I don't know why I keep doing commas. And this is our final domain. So yes, in this video today, we kind of described how to combine functions. We talked simply about combining functions using arithmetic operations, as well as scaling by a scalar. And then we talked about composition functions, what they are, how to use, and most importantly, just remember the domain of composition functions. That's where I see a lot of people tripped up, but it's not too hard if you really think about it. All right, thanks. That's all for today. Thanks for listening, and I'll see you in the next video.